Hello everyone, I'm Kuan from University of Oxford. Today I'd like to talk about counting solutions to random CNF formulas. This is a joint work with Andreas Galanis, Leslie Goldberg, and Heng. Now let's start from a brief introduction to CNF formulas. A CNF formula consists of some clauses, which are connected by AND. Each clause consists of some literals, which are connected by OR. Each literal is a positive or negative form of a variable. For example, here x1 to x4 are called variables. x1 or not x2 or x4 is called a clause. A K-CNF formula is a formula where each clause contains exactly k literals. In this talk, we consider random K-CNF formulas. We use phi KNM to denote a random K-CNF formula on n variables and m clauses, where each literal is chosen uniformly at random from v1 to vn and not v1 to not vn. We also use alpha to denote the density of the formula, where alpha is given by m over n. Here is a natural question. Does there exist an alignment to variables that can satisfy all clauses of phi? This question has been well studied. The answer was given in 2015. There exists a number alpha star, which is roughly 2 to the k times log 2, such that if alpha is less than alpha star, then when n goes to infinity, the probability that phi is satisfiable goes to 1. Otherwise, if alpha is greater than alpha star, then the probability goes to 0 as n goes to infinity. This result was proved by the second moment method, which is a non-algorithmic method. So we still have some algorithmic questions. The first is that, can we find a solution for phi when alpha is less than alpha star? There was a work in 2009 that gives an algorithm where alpha is less than roughly 2 to the k times log k over k. This algorithm works with probability 1 minus small o1 over the choice of phi. However, in 2010, a strong evidence shows that the problem is hard when alpha is greater than roughly 2 to the k times log k over k. So, the solution space undergoes a phase transition at this threshold. The second algorithmic question is, can we count z, which is the number of solutions of phi when alpha is less than alpha star? In statistical physics, people are interested in 1 over n times the expectation of log z. However, there is no known formula apart from the case k equals to 2. In fact, this problem is hard in general. So we ask the following question instead. Can we approximate the number of solutions of phi? In 2007, Montanari and Shah gave an p-task for 1 over n times log z, where alpha is less than 2 times log k over k. Here, p-task means that the algorithm only gives an epsilon approximation to 1 over n times log z for constant epsilon. Can we do more precise approximations? What we want is an fp-task, which can produce an estimate z hat within 1 plus and minus epsilon times z in time polynomial of n and 1 over epsilon. Moreover, can we handle bigger values of alpha? Note that their algorithm only works when alpha is very small. However, alpha star is an exponential of k, so there is a huge gap. Now let me introduce our result. We showed that there exists a deterministic algorithm A and two constants R and K0 such that for all sufficiently large k, and as long as alpha is less than 2 to the R times k, with probability 1 minus small o 1 over the choice of phi, our algorithm on input phi and any epsilon greater than 0 outputs a number z hat such that e to the minus epsilon times z is less than z hat less than e to the epsilon times z. Our algorithm outputs such number in time polynomial of n and 1 over epsilon. Our method is based on approximate counting via estimating marginals. This is a widely applied subroutine. Here is a brief introduction. Let mu be the uniform distribution over all solutions of phi. Assume that phi contains n variables from v1 to vn, and tau is the satisfying alignment of phi. Then let pi be the marginal distribution of vi, conditioned on that v1 is fixed to be tau v1, v2 is fixed to be tau v2, and so on. Then z is equal to 1 over the product of pi. Now our goal is to approximate the marginal probability pi. Unfortunately, brief propagation type algorithms don't work well for computing pi. Because these algorithms rely heavily on correlation decay properties for arbitrary conditions. However, even in the case of monotone k-CNF, this property cannot be guaranteed if alpha is large. Our algorithm is based on the approach used by Moitra in 2017. Moitra gave them f-pitas on bounded degree formulas. Here, the degree means the number of clauses that contains a variable. However, for random formulas, there might be some variables occur in many clauses. So the key difficulty for us is to control the effect of high-degree variables. First, let's review Moitra's method. Moitra first divided variables into two sets, marked and unmarked, such that every clause has at least k over 4 marked variables and at least k over 4 unmarked variables. And there exists a partial alignment tau prime only on marked variables that satisfies all clauses. Note that the existence of such sets and partial alignment tau prime are guaranteed by Lova's local lemma. Then, Moitra approximates marginals only of marked variables. Assume that v1 to vt are marked variables. Then, z is equal to 1 over the product of vi times 2 to the number of unmarked variables. Here is the key factor used in Moitra's analysis. After fixing marked variables, clauses are still not too short. So again, applying Lova's local lemma, we can obtain that for every variable v, the marginal PV satisfies that PV is sufficiently close to 1/2. Then let's review the method of approximating the ratio between marginals of a variable v star. Let mu1 be the distribution conditioned on that v star is fixed to be true, and v2 be the distribution conditioned on that v star is fixed to be false. Consider the following coupling between mu1 and mu2. Let A1 and A2 be two partial alignments. At first, A1 v star is true, and A2 v star is false. We also maintain a set Vi, which, roughly speaking, contains the variables that cause the coupling fail to terminate. Vi starts from an isolated variable, v star. At each time, pick a clause C that contains variables from Vi. Then assign values to marked variables in C in both A1 and A2 one by one, according to the conditioned probability, and couple them maximally, which means we try to assign the same value to them in A1 and A2 as far as possible. Then, if the value of some variable v disagrees in A1 and A2, we add v into the set Vi. If the clause C is not satisfied on the A1 or A2, add all variables in C into Vi. Finally, go to step 2 until there is no such clause C. Recall that the conditioned distribution is close to the uniform, so Moitra shows that the probability that the size of Vi is at least t times log n is less than 2 to the minus t, which yields that the coupling process terminates quickly with high probability. However, we cannot implement the coupling process directly, so Moitra constructs a coupling tree to enumerate every possible path. For each node, he assigns two quantities Pi1 row and P2 row. The key observation is that Pi row and the ratio between marginals of V star satisfies some linear constraints. So Moitra can use linear program and binary search to approximate the ratio. Note that the key step in Moitra's analysis is that the degree bound delta allows to show that marginals are close to 1/2, and therefore the coupling succeeds with high probability quickly. However, for random formulas, for any constant delta, a linear fraction of variables have degree at least delta. Actually, the maximal degree in random formulas is of order log n over log n. Unfortunately, high degree variables can have marginals arbitrarily close to 1. And furthermore, there is potential domino effect. If a variable is in a clause with many high degree variables, the variable itself becomes potentially constrained as well. How can we address problems for random formulas? Our idea is to somehow ignore these bad variables and only consider good variables. We only approximate marginals of good variables, and then we hope that the bad variables are not concentrated with high probability. To control the domino effect, we define bad variables and clauses. First, high degree variables are variables of degree at least 2 to the k over 300. Then we identify bad variables and clauses using the following process. First, high degree variables are bad variables. Second, clauses with at least k over 10 bad variables are bad clauses. Next, variables contained in bad clauses are bad variables. Then we go to step 2 until there are no new bad clauses. Finally, every good clause contains at least 9k over 10 good variables. But for every bad clause, all variables are bad. Applying some existing result, we can claim that with high probability, the number of bad variables is at most n over 2 to the k to 10. Now let's consider the marking process. Note that we only mark good variables, and our partial alignment top prime only satisfies all good clauses. So we need to compute the number of satisfying alignments to bad clauses. However, bad variables are too bad, so we cannot hope any good properties to help us count the solutions. We compute by enumerating all alignments to bad variables. So we require that bad components must have size at most O log n. Here, a bad component is connected component in the fact graph of phi, induced by only bad variables and bad clauses. Next, let's consider the coupling process. During the coupling process, if we encounter a bad variable v, then add all variables in the same bad component into vi. Recall that when we couple mu1 and mu2, we pick a clause C that contains variables from vi, then align values to marked variables in C in both A1 and A2 one by one. Now, if V is bad, then add the whole bad component into vi. Otherwise, if the value of V disagrees in A1 and A2, add V into vi. If C is not satisfied, then add all variables into vi. Now, to control the size of vi, we require that first, again, bad components have size at most O log n. Second, a connected set do not have too many neighbors in the factor graph. Otherwise, there might be too many bad components added into vi. Finally, I'd like to briefly introduce some key properties of random formulas that we used in our analysis. First, let's consider the factor graph of the formula. Here, squares denote clauses and the circles denote variables. Two clauses are connected by dashed edges if they share a same variable. Here, gray clauses denoted by set X are connected by dashed edges. Green variables denoted by the set U are contained in gray clauses. Blue clauses denoted by set Y contain green variables. Then we can show that if the size of X is at least log n, then with high probability, the size of U and the size of Y are upper bounded by a constant times the size of X. This property has two corollaries. The first is that every connected set in the factor graph do not have too many neighbors. The second is that an omega log n size connected set of variables cannot have many high degree ones. Next, let's see the second key property. Consider the process that identifies bad variables. Suppose that gray circles are high degree variables and green circles are bad but low degree variables. We use H and B to denote them respectively. We can show that with high probability the size of B is upper bounded by a constant times the size of H. This property also implies two corollaries. The first one is that with high probability, we do not identify too many bad variables in a random formula. Second, combining with the first key property, it yields that the size of any bad component is at most all of n. So far, we perfectly obtained what we want. At last, I'd like to talk about some open questions. Note that the bound for the existence of satisfying alignment is alpha is roughly less than 2 to the k times log 2. The bound for finding a solution is that alpha is less than roughly 2 to the k times log k over k. Our result requires a bound roughly k is less than 2 to the k over 301. Our constant 301 is not small enough. Is it possible to improve our bound or find a hardness result? Note that there is no known hardness result for random formulas, but for bounded degree monotone CNF, we have a hardness result if delta is at least 5 times 2 to the k over 2. There are still some open questions. How about small k? For example, 3 set. Note that we use the Nova's local number, which requires sufficiently large k, so our method cannot apply to small k. In addition, how about great k? When k is not a constant, can we still obtain an algorithm in time polynomial of k? For bounded degree cases, there is a sampling algorithm and thus a randomized counting algorithm in time polynomial of k. Can we improve our result for greater k? That's all. Thank you.